Greetings. Welcome to our 23rd episode of the FGI podcast series. My name is Tim Stark, and I'm a professor of civil engineering at the University of Illinois at Urbana-Champaign.
And hello, everyone. My name is Jen Miller, and I'm the coordinator of the Fabricated Geomembrane Institute, or the FGI.
On today's episode, we are going to focus on our January 14th, 2021 webinar titled Yeager Airport Reinforced Soil Slope Failure Case History, Forensic Limit Equilibrium, and FLAC Analyses. I'd like to quickly reintroduce our speakers. Jim Collin is the founder of the Collin Group and is an expert in reinforced soil structures. Augusto Lucarelli is a principal engineer with Itasca International in Minneapolis and has extensive experience with continuum deformation analyses using the software package FLAC. Okay, Jim and Augusto, thanks so much for joining us again. We received many questions during and after your webinar on the Yeager Airport failure. So, Jim, I'd like to start with you, and you have about 12 questions. Jim, would it be possible to install a double layer of the geogrid, one in machine direction, one in the other direction or cross machine direction, to cover the weakness of the material in the transverse direction that was used at the site?
Yes, that is an approach we typically use when we have loading in two directions and we need a high strength material. So that certainly could have been one option for the designers. I'm not going to suggest that was the only option, but that's something that they could have considered.
Okay. Does the geogrid market, offer this material made by polyester high strength threads? Would that have been a better geogrid to use?
The geogrid used on this project was a polyester geogrid.
Oh, okay, great.
All right. Jim, does the 90% reduction in geogrid tensile strength at a 60-degree skew refer to the ultimate strength or strength at 5% strain?
That was based on the ultimate strength of the grid.
Great.
Okay.
Wouldn't the lateral discontinuities, i.e. the roll widths, be more significant than the anisotropic grid strength?
Well, that's an interesting question. The roll widths, the grid was continuous at the face of the slope, and so then it overlapped in the back. Where the failure surface didn't really cross over the discontinuities between the roll widths. We didn't see that as an issue.
Okay. Were they like zip tied together or just laid on top of each other? Or next
just laid on top.
Yeah.
There was no connection.
Great. How are the strengths and directions neither perpendicular nor parallel to the machine direction determined? Were these available in tables from the grid gear manufacturer, or did you conduct project-specific testing to determine this?
We did specific testing at TRI laboratories where we ran the test at the machine direction, the cross machine, then at 60 and 30 degrees from those.
Right. Would use of biaxial grids, if of adequate strength, have helped avoid the anisotropic strength reduction? And that gets back to a question before, sort of.
Yes, it would have. But traditionally, we don't have such high strength biaxial geogrids, but certainly one could have been manufactured.
Is it known if any triaxial geogrids were considered in the original design?
The triaxial grid is a lightweight grid that doesn't have strength, so it wouldn't be appropriate for this design. And back in 2005, when they were designing and constructing this, I don't think the triax was available at that point.
Okay. Jim, there are a couple questions here in a row about drainage, and mainly referring to drainage at the back of the reinforced soil mass. So first question, any provision of subsurface drainage in the form of geotextile wrapped gravel chimney drain at the interface of the existing slope and the new reinforced soil slope?
The original design did not include any drainage for the structure, and the reinforced fill had a gradation allowed up to 50% fines. So this was a criticism. The material they actually used had much less fines. It wasn't free draining, but it had a permeability. So there was no drain in the original design. During construction, a couple locations, seeps were noted, and a drain, as described in this question, stone wrapped in a geotextile, was done to capture that and bring it out to the sides of the slope.
Okay. What benefit would have been if a drainage layer had been installed at the back of the reinforced soil mass, and that could even have been a vertical drainage layer up the back slope?
Well, to minimize the water that did get into the reinforced soil slope. So the geology was such that the sandstone that was behind the reinforced slope, the joints in that brought water right to the back of the slope. We had no piezometer readings prior to failure to determine what the groundwater was, but certainly the impact of that water on the failure surface was probably contributed to the degradation of that claystone at the failure surface.
Right. Was there any reduction considered for environmental effects, for example, pH level of the groundwater soil for the geogrids?
Well, the design, I believe, used a reduction factor of 1.1, kind of the standard. When we did our analysis, when we exhumed the grids and tested those for strength, that strength that we tested included any degradation from installation damage or environmental effects. So we included that if there was any in our analysis.
Okay. Last question, Jim, and it's sort of a loaded question. What would be the one thing that the designer would have done to protect the failure significantly? In other words, what could they have done to prevent the failure?
Well, if you read our papers and our report, there were many things that contributed to the failure. So I don't know that I could say there's any one specific one, although I think in some of the questions that are come up next, if they had designed for a higher factor of safety, that might have been the one thing that would have overcome all of the other issues that they had. The design factor of safety is 1.3.
Yep. Okay.
That's great. Thanks, Jim. All right, we're going to switch gears, and the next few questions are going to Tim. So, Tim, one of the questions we received is, what are L1, G1, and S1, and what do they denote?
So L1, G1, S1, and there are a couple other numbers like G2, S2, and S3 denote the length of the grid, so that's the L. The G is the geogrid strength used in the analysis, and there were 3 of those. And S is the soil strength that was used, and there are 3 of those. So L1 is the first length of grid used, which is 175 feet. G1 is the first strength, which was the long-term design strength used by the designer, and that included installation damage, degradation, and creep. And S1 is the first strength, which is the peak strength used by the designer of 36 degrees. Next question is, what are the elevations of the low, medium, high groundwater levels that were considered in the slope stability analyses? So first was dry, which is 0. High groundwater is about 10 meters above the back or the failure surface. Medium's about 6 and low is about 3. Now, that groundwater level varied from the toe up the slope. So at the highest point are those numbers. It's lower at many other points in the cross section. However, the analysis showed that the factor of safety is not that sensitive to the groundwater level indicated. These water pressures were acting on the clay shale interface, so in other words, the failure surface in the limit equilibrium, both 2D, 3D analyses. Next question is, when we have complex geometry, is a 1.5 factor of safety for 2D enough? And Jim sort of touched on this already. The design was 1.3, which is too low. 1.5 is maybe suitable for a typical slope. This was not a typical slope. It had anisotropic geogrids in it. It was an unprecedented structure. There was a lot of uncertainties associated with the design and certainly the toe of the slope. The criticality of the slope, it's located just above a inhabited area, and of course the cost of remediation and the impact on the airport. So a reasonable factor of safety for 2D was probably around 2. In the 3D analysis I showed in the webinar, you would need a 3D factor of safety of 1.9 at least to even get to a 2D factor of safety of 1.5. Next question is, what is the displacement in the field needed to mobilize the fully softened strength and the residual strength? The displacement for fully softened strength is 0. All you need for fully softened strength mobilization is moisture and sort of wet-dry cycles and the soil absorbing that moisture, and it softens from its peak strength, in this particular case a compacted peak strength, to a fully softened strength. The residual strength, you do need some shear displacement occurring in the field. In the laboratory, in a ring shear device, you would need, say, 6 to 10 inches of displacement to get the residual. In the field, it's probably around that or even smaller if it's focused on a shear surface, like is what developed at the back of the reinforced soil mass. Could the soil strength softening occur due to strains from slope settlement? In other words, wouldn't the current slope design have failed regardless of water pressure? So the first part of that question is, the softening will occur without deformation. But as the slope settled or moved down towards the toe, it would pass the peak or the fully softened strength and go to residual. So you would be going to residual, not fully softened with those strains. The slope design would have failed regardless of water pressure. That's the analysis. The analysis shows the factor of safety was not that sensitive to the water pressure. Okay, we have a couple questions for Augusto Lucarelli, who performed the FLAC analyses for the case. Augusto, would you discuss some of the more interesting modeling components for this project, such as the shear strength envelopes and strength reductions for the failure surface or the interface properties?
Yeah, interesting question. It would require probably a little bit longer than a minute, and there are many interesting aspects. I would say that just in a summary, the nonlinear strength envelope is well defined by a power law, and I think probably the most interesting part is the implementation, which is essentially a linearization of the power law into a more Coulomb equivalent. So essentially, what you would do, you would keep track of the principal stresses, keep track of the Mohr circle during the analysis, and then linearize at the current stress level, let's say the center of the sinker, for example, for easy of visualization, and then draw a vertical line and determine the tangent, which is the apparent friction angle, and then from the tangent draw the intercept, which is let's say an intercept cohesion. These are numerical parameters. They are not physical friction angle or cohesion. They're just the derivative and the intercept for sigma normal equals 0. The interface is the sensitivity that I did probably was the interface for the cable element that was modeling the geogrids. I didn't see a significant impact, and also for the stiffness of that interface, we didn't see a significant impact on the results.
Great. Next question, Augusto. It has been recognized in recent work that strain softening may result in mesh dependency. Was there any further validation to the FLAC model other than location of the failure surface, and were there wet-dry cycles modeled in your analysis?
Okay, so a couple of these 2 points. The wet-dry cycles were not modeled. As far as the strain softening and mesh dependency, yeah, it is a very good point, and it is mostly relevant when you don't know where the shear, where the failure would occur. In this case, we know where the problem was, and I did some sensitivity analysis in terms of mesh size inside the shale or weak zone, and once I saw that we have at least 3-4 zones inside the thickness of that element, I didn't see any significant change in terms of reduction factor. So in principle, it is something to keep in mind. In this case, it's probably not so important.
Okay. And back to the wet-dry cycles, Augusto, you sort of indirectly modeled that because you started with a peak strength of 36 degrees, and then you dropped or reduced the strength, the nonlinear strength envelope, towards the fully softened envelope to simulate basically the softening from the wet-dry cycles, right?
Yes, if we want to look in that way, yes, it is an indirect way to do it, but I thought that the listener was asking for a complete, fully wet cycling, drying modeling, so with a different constitutive model. No, in that case, that was not the answer.
Yeah, right.
But yes, in a simplified way, we did it.
Right, exactly. Okay, well, great. Thank you to Jim and Augusto for joining us again. That's all the time we have. If you have additional questions, please contact Jim or Augusto. Their contact information is in the PDF for the webinar, or you can email me, and I will send the questions to them at fabricatedgeomembrane@gmail.com, or visit the FGI website at fabricatedgeomembrane.com. Jim and Augusto, thanks so much for joining us again.
Thank you.
See ya.
Thank you.
Goodbye, everyone.
Bye.